When deriving the equations of motion with linear drag, we had a bunch of different variables, most of which we knew, like the mass of the object and the gravitational acceleration, but one of them that we didn't know was the constant of proportionality. So recall that drag is going to be equal to minus kv. What is that k? So most of the time this is done using experiments, but we can figure it out using this method, which kind of assumes some things that other people have done from experiments, but I don't have all the equipment, so this is how we're going to do it. So the terminal velocity is defined as the square root of 2 times the mass, m is mass, times g, which is the acceleration due to gravity, over rho, which means the density of the fluid, a, which is the cross-sectional area, and cd, which is the drag coefficient. So for a golf ball, it'll be our first example. We have m equals 0.046, and that should be kilograms, because they all have to be in SI units, and the SI unit for mass is kilograms. Gravitational acceleration, we're going to assume it's on Earth for now, is 9.8 meters per second squared. Rho, the density of the fluid, and the fluid we're going through is just normal air. It's about 1.293 kilograms per meter cubed. The cross-sectional area, well, it's going to be a sphere, so the cross-sectional area is just the area of a circle, which is pi r squared. So that's pi multiplied by the radius of a golf ball is about 0.0213 meters. Again, has to be in SI units, had to be meters, not centimeters. And you can look up all these values online, but it's a lot of different links, so I'm not going to list them in the sources. Anyway, when you evaluate this, you get pi times this squared. You get about 0.0014 meters squared as the cross-sectional area, and the coefficient of drag is about 0.25. Now, where did I get this from? Well, that's what I'm going to show you. So, if we go down, I found one of these charts while I was researching. So it shows how the drag coefficient is here on the left, and then Reynolds number is on the bottom. So I'll explain what that is in a second, but as you can see, for a smooth ball, it's actually a lot higher up here, and then it goes all the way down here for high Reynolds numbers. But for a golf ball, it's a lot lower, and that's because of the dimples, and that's why golf balls actually have dimples. Anyways, so Reynolds number is just this special number that's used in fluid dynamics, which is basically how things move through fluids. It's kind of really complicated, but basically it's defined as UL over V, where U is the velocity of the object. Well, it's technically the velocity of the fluid with respect to the object, but in our case, it's just going to be the velocity of the object to make it simpler. L is the characteristic length, which is the volume over the surface area, and V is the kinematic viscosity of the fluid through which it's traveling, which for air is about 0.0000152, and that's at 20 degrees Celsius, because it actually depends on temperature. But I'm going to say 20 degrees Celsius, because I think that's a good standard temperature. So if we're going to look at the characteristic length now, so for a sphere we have the volume is 4 over 3 pi r cubed, and the surface area is 4 pi r squared. So volume over surface area is 4 over 3 pi r cubed all over 4 pi r squared. So we can cancel the pi's. We can also cancel the r squared, leaving us with just one r up here. And then we can also cancel the 4's, giving us a third of r is the same as L. And then the radius of a golf ball, we said earlier, is about 0.0213 meters. So we have a third times 0.0213 meters. And that is equal to 0.0071 meters. So we can fill that in. So now if we put this into find the Reynolds number, we have RE equals... So the velocity could be anything, so I'm going to leave that for now. So we have L over V. So L we just figured out here is 0.0071 divided by V, which is about 0.0000152 multiplied by U, and that's about 467 U. Not exactly, but we're going to say that the Reynolds number for this golf ball is 467 U. Well, it should be for most golf balls. So now what does this mean? So U is the velocity. Now I did a bit of research and I found that when you're hitting a golf ball, most of the professionals, and I think just most players in general, would hit them at least like 40 meters per second, which is about 100 miles per hour, or just under 100 miles per hour. So 40 meters per second is the average. So if we go back up to the graph, we can see that at 10 to the 4, the drag coefficient's really high, but just before 10 to the 5 for the Reynolds number, the drag coefficient's about 0.25, and it kind of stays down there for bigger numbers. I don't know why it doesn't continue on, but I think it just kind of continues on in that straight line. So if we have a look, if we set the Reynolds number to 10 to the 5, or it'll be just under 10 to the 5. We can say that here is maybe, I think that might be like 4/5 of the way to 10 to the 5. So that's going to be about 8,000. So if we set the Reynolds number to be 8,000 equals 467 u, that means u, our velocity, is going to be 8,000 over 467, which is approximately equal to, that's approximately equal to 17 meters per second. And as I said, the average golf ball swing is like at least 40 meters per second. So this is way under 40. So I think it's very safe to assume that the drag coefficient is going to be around the 0.25 mark, which is why I've said the drag coefficient is going to be about 0.25. So now we can finally fill these into the equation for the terminal velocity. So V terminal equals the square root of 2 times the mass is 0.046 times g is 9.8 in this case, all over rho, which is 1.293, times the cross-sectional area, 0.0014, multiplied by the coefficient of drag, 0.25. This is approximately equal to 44.63 meters per second, and if you look it up, I found a lot of different results for the terminal velocity of a golf ball, but a good few of them were around 45, so I'd say this is a good approximation. So we're going to use this for our terminal velocity. So now you might be thinking, what does terminal velocity actually mean? Well, basically, when you drop an object, it's going to keep accelerating downwards due to gravity, but eventually it's going to reach a point where the drag force, which goes against the direction of motion, so if gravity is pulling it down, the drag is pulling it up. There's a certain point at which the drag force cancels out the force of gravity, and it's not accelerating anymore, which means that the acceleration is equal to 0. So if we just consider a ball going down, so if we just say there's a ball, and it's going downwards due to gravity, so this is its weight pulling it down, which is equal to mg, and then you have a force pulling it up, which is the drag force, which is equal to minus kv. Well, we know the forces, the sum of the forces equals ma, and that's going to be equal to mg minus kv. Just in this case, if we say that mg going positive is down and going up is negative, and then we know at terminal velocity, so at vt, the acceleration will be 0. It won't be accelerating anymore because the forces are cancelled out. So now we have ma equals mg minus kv, and this a is going to be 0, so this all just cancels, and we get we get 0 equals mg minus kv, which means we get kv equals mg. Sorry, this is at kvt, because we said this is going to be at terminal velocity. So now if we want to find k, we can say k equals mg over the terminal velocity, which is equal to, so the mass we said was 0.046 kilograms, multiplied by gravity, which is 9.8 on Earth, all over the terminal velocity, which we said is 44.463. That's approximately equal to, so that's about 0.01. So this is what our value of k is going to be if we're looking at a golf ball. And key point, this is for a golf ball. It actually is going to be different for every other object we look at. So if we apply the same thing to a basketball, we get that the terminal velocity, vt, equals the square root of 2 times the mass is 0.625, that looks like a 0, times g is 9.8 on Earth, all over the density of air, 1.293, that's also the same, times the cross-sectional area, 0.1385, times the drag coefficient I found to be 0.54, using similar methods as last time, and all of that's approximately equal to, so that gives us approximately 11.26 meters per second. Now the thing is, when I googled it, it said it's 20 meters per second, but I got 11, and when I looked up the terminal velocity that other people got after calculations, it was also around 11. So I don't know, I'm going to calculate the value of k for 11 meter per second terminal velocity and for 20 meter per second terminal velocity, just to see what it is. So as I said earlier, this is going to occur when mg equals kv, as we showed earlier, kvt, sorry, which means that k equals mg over vt, which is equal to the mass is 0.625 times g is 9.8, all over, we're going to do 11.26 for now. That's approximately equal to, so this was given us a coefficient of 0.54, which is very high compared to the last one. I'm not sure how accurate this is. And then if we do it for the 20 meters per second terminal velocity, we get 0.625 times 9.8 over, let's say 20, which is approximately equal to, it's approximately equal to, that's about 0.3, which seems more, 0.31, which is a bit more realistic, but you'll see later that both of these kind of don't really make sense, but we'll put a box around them anyway, and if anyone knows what's wrong with this, please let me know, and yeah, I'll see you in part 4.